presentations, and now I will leave the floor to Giovanna. Giovanna, you want to come here?
Dave, you can also introduce.
And yes, both of you. So if you want to, sorry, this.
I'm going to do this very shortly. Welcome to Iceland. Welcome online. Welcome to the H-Hope community. Welcome to our guest speakers. I'm going to give the floor to Giovanna. Welcome to Iceland. Thank you very much.
Thank you very much. So I also repeat the words of David. Welcome to everybody here and online. We are very proud of this first event, whose goal is to engage stakeholders, because we really need feedback from you. We really need information and your opinion on what you are doing, since we are just at the end, almost at the end of the first year of a project. We have still a lot of things to do and a lot of activities to carry out, and it's important to properly drive the activities in a direction which could be useful for the potential users of our technology, because otherwise it makes no sense. So I do not want to waste more time. I think it's time to start with the presentation. So Steve, leave you the floor again.
It would be useful to... Can we have this one? So in the meantime, I'd like to share a video of the project. So we have a bit of an introduction of what the project is all about. So I'll be actually sharing with you right now a video of our project. This is essentially a project, again, funded by the European Union. And it has been basically, we started in November of last year, and we'd like to show you a video of the project so that you can have an idea of what actually we're actually doing. So let me just share my screen again.
Perfect.
So that was a bit of an introduction to the project. And again, we're happy to share this with you and to introduce our first speaker for today. As I take out the presentation, I will invite both our colleagues to come to the stage.
So, oh well, I'll introduce you first, maybe. Sigurðardóttir, my colleague in Veiter. Like to just...
Yeah, so My name is Sigríður or Sigga. I've been at Veitur for 4.5 years. I joined the company as a modeler because we didn't have a single hydraulic model of our systems. Lilja will tell you a little bit more about what kind of systems we're operating, but basically 4 different utilities. So my job was to create these models, and we've really disrupted how we take decisions at Veitur. I'm going to tell you a little bit about that. But now things have been good at Veitur, and now I lead the team of digital development. So it's like the group of people who are trying to create value from our data, which comes, well, I would say mostly from the different meters that we have in our system. So yeah, that's me.
Yeah. Thank you. I'm Lilja Tryggvadóttir. Most of you know me, maybe not all. I am an engineer, so mechanical engineer, and I'm also a research project manager with Reykjavik Energy and work there in the research and development. And we're going to introduce to you our smart metering journey to improve water management. And we are an old company, Reykjavik Energy. It dates back to 1909. And it's a public company owned by 3 municipalities. And the renewable energy generation has been ongoing since 1921. And that's the hydropower plant in Elliðaárdalur that some of us visited yesterday. And we serve about 75% of Icelanders in some shape or form, as we would get into later. And we are also the world leader in CO2 sequestration through our CarbFix daughter company. And the catalyst in Iceland's energy shift in transportation through ON. So you see here the daughter companies on top, if it can be seen. There we go. Veitur, Ljósleiðarinn, the fiber optic company, ON Power, that has the geothermal power plants, and CarbFix. And the mother company is depicted below, as we see us serving the daughter companies, and not the other way around. Okay, there we go. Okay, so we connect people and natural resources. And this is just to show the different utilities that we have and the approximate percentage of households served. So we have the water reserves, which is of course then the groundwater, the watershed as well, and the waterworks and the distribution to the homes. And it's about 40% of the homes that are served by that. And as you can see, also the blue line continues on through the sewage and out to the ocean. In low temperature geothermal, we have the district heating network serving about 70% of the population. And it goes through the tanks. You have seen probably the tanks below the pearl here next to the university where we are, we who are here. And then to the heating the homes and industry, and also then through the sewage out into the ocean. And in high temperature geothermal, we have the power plants, and they also serve warm water or hot fluid to the district heating network. And hydropower joins in for the electric distribution system. So we also have the electric distribution utility and serve by that about 60% of the population. And last but not least, the fiber optic company serving 65% of the population. So as you see, we have many different utilities, many different resources to watch over and manage to be able to operate our networks. And we like to say that we operate them responsibly, or that is always our goal with all our work, to have a responsible operation of the resources. And here you see also like an overview picture of the different systems on first. The logo mark on the map shows where Nesjavellir geothermal power plant and Hellisheiði geothermal power plant are located. 200 megawatt thermal and 300 megawatt electricity in Hellisheiði, 340 megawatt thermal and 120 megawatt electricity in Nesjavellir. Then we have the district heating network, and there we have 13 separate systems that we are operating, and it's about 10,000 kilometers of pipes. And Reykjavik alone has 5,500 liters per second of 84 degrees Celsius water. That is, if you recalculate the water to 84 degrees, it's about 5,500 liters per second, or 1 gigawatt thermal. And of course, there's also the water distribution system, electricity distribution system, and sewage system. And you see the different colors of the do you see if I do like that? Yeah. So you see the different colors there, and the different colors also within the map. So by that you can see where we are serving what kind of service. And now I give the floor over to Sigga.
Temporarily.
Temporarily.
Thank you, Lilia. So yeah, I'm gonna tell you a little bit about the smart meters and how we see the value and the data that it will bring to us. But we're currently rolling out the smart meters, and like you saw the map in Lilia's picture, so I'm not actually capturing whole of the area, but this is like where the most of the population is. But the green areas is where we've finished replacing the old meters with smart meters. And then the rest is going to be finished within the next 2 years. So where we stand in the project right now is that this is like in terms of replacing the meters, but we're still like not ready with our IT department is basically working on bringing it in-house, like the data in real time. So right now we've only been looking at the data in like with data dumps. But we're super excited, and that's going to happen within the next few months. Like the timeline is November. So anyway, it's a huge investment. It's a huge project, but we are doing it because we see benefits from it. And maybe the most obvious benefit for our customers right away is that they will no longer have to submit the readings from the meters to us at least once a year, and responsible consumers maybe do it more often. So that's gonna be the most obvious change to many to begin with. But also it's gonna change the way we bill our customers. They will be invoiced exactly for what they use each month. Instead of the old estimations that we've been using, leading to some corrections in the end of the year. So I think that's gonna be a big change. Also, it creates the opportunity to catch some problems or inconsistencies that you can see in the energy usage, maybe caused by faulty electrical devices. So at the end of the year, you're not going to get like a huge bill because you have something, you have some problem at your home. You're going to see it right away. But the way we see it, it's like I think the biggest benefit from all of this is that now finally our customers will get the opportunity and the tools to really understand how they use their energy. And with that, they can get the ability to change it and change their behavior. And there are further benefits. Mostly we see that it's going to support our investments, so we can better prioritize the funds that we have to upgrade the system. I mean, with this new data, we're going to get a much clearer picture. But during those outages that will, of course, still happen, we foresee that the response is going to be much faster, so we can pinpoint right away and locate where there's a problem. And yeah, last but not least, with the smart meter data, we will just finally get a very holistic view of the quality of the service that we are providing, like hopefully a confirmation that we are indeed delivering as we promise. Yes, I'm a woman of simulation models. That's my expertise, and I can proudly say that to realize some of the benefits that we hope to get from the smart meter data, we need the simulation models, which we are using currently. But what's going to happen with the smart meter data is that we're going to get much better and more accurate models. And with these models, we can get better insights to our systems. It really changes the way how we see things. So we can map where the system is maybe reaching its limits, identify bottlenecks, and thus, like I mentioned earlier, prioritize our funds. Like we want to be sure that we're always investing where the need is urgent. And if we know that we are always upgrading the system where the need is, where we need to, we hopefully move more to predictive maintenance instead of being reactive, which we in the past have been quite guilty of. And that, of course, means that the operations are going to be more stable. And then, of course, it's always, in the end, it's for our customers, and this will hopefully mean better service. And yeah, actually, a very big point as well. It's helping us to support it's supporting the resource management as well, which is Lilja's expertise. And then with these models, if you have a precise model of your system, you can basically test any scenario you can think of. And I'm going to show you one of the bigger projects that we've been doing using these simulation models. Because we live in a city that is always expanding. There are like many densification areas where like putting houses everywhere there is some space, and of course we need to connect these new customers to our systems, and these models are helping us enormously to sort of plan ahead, because the city has quite ambitious plans on expanding and getting bigger. And so what we did is that we went through all the planning data for Reykjavik and the surrounding municipalities, and we located all the new neighborhoods and the densification areas of the city. So basically, we found out where are we going to be seeing new houses and buildings, and then we converted that into what it means to us, which is like more demand for electricity, hot water, and water, and maybe sewage. But in that system, we're mostly worried about intense rain events. But yeah, so we converted this planning data basically into the future demand, and we have these planning data like 40 years ahead of us. So we could, with the simulation models, we could have a look and see like what's going to happen to our system. And well, this is maybe not the final results, but this is like what it looks like, because we have, of course, many utilities, and then we have like many time intervals with this data. So we're looking at like what's going to happen in the next 5 years, 10 years, and so on. So we do it like in steps. But this is basically what we did, and we have results for this like for different utilities and different time intervals, like next 5 years, 10 years, and so on. So in each zone or area, depending on the result from the simulation, we looked at how it's going to affect our system. And we rated it either green, yellow, or red. Green meaning that it's just like a normal connection for us, nothing big. Yellow means that we have to maybe strengthen the system a little bit, make some investment. While red means that we have to go into bigger investments and large projects. It might take a few years. So this is a really nice tool to go into conversation with the municipalities, so like we can, you know, do this as a team. And then finally, what I'm super excited about, which is like what we're gonna do to take these models to the next level, is that we're gonna create what I call and we call a digital twin, as it's a very much a buzzword these days, and everybody has their own definition of it. Our definition means that it's real-time model of the system. So we've done like a small pilot, which we're gonna expand during the next weeks. And with when the smart meter data starts rolling in, it's gonna be even more reliable. But basically, it means that we take the model that we have and connect it with live data. So basically, we can have a look at what's happening in the system at any time. And this becomes a tool we can sort of deliver to, for instance, our customer call center, which like right now they are constantly taking, if there's a problem in the system, it's usually the customers who are letting us know. But we want to be proactive and see things before they happen, before the calls come in. So we could maybe call the customers before. So yeah, we have very sort of promising results from the pilot. And yeah, and finally, this is also going to be a very useful tool to pinpoint and locate leakages fast. So that was what I had to say. Thank you.
And this, of course, sounds like we have the whole world mapped, which is maybe not quite the case.
Almost.
But almost. So we're heading there. And of course, there are some points that we can still improve. And one reason why we are in the H-Hope project is, of course, that. And we would like to be part of this group that is solving how to meter where we do not have the electricity to meter, for example. And we are now searching for the H-Hope case study within our system. And we had a lot of discussion with work package leaders within the group on constraints, because of course, when you are simulating the real environment within a laboratory environment, you need to have some constraints and you have some limits. And then after that, we had 2 internal workshops with our main district heating experts and research team that know our system inside and out. And the constraints are not really beneficial for our district heating network, was really the end result. Because we have so warm fluid, our fluid is hotter than 80 degrees and our pipes are quite slim. So we needed to be over 200 millimeters, they wanted really. But we also continued, of course, looking at the system, and this is the system that we are looking at. So water temperature, 80 to 130 degrees, pipe diameter it's of course very varying. So from 32 to 900 millimeters. We have the 2 main veins, so to say, coming from the power plants to the city, from Nesjavellir and Hellisheiði, 24 kilometers of a 900 millimeter pipe with 1500 liters per second from Nesjavellir, and then 19 kilometers of the 900 millimeter pipe with 1000 liters per second. So these are like the big veins coming into the city. And of course, that would be the dream, that when we have innovated enough, we can have the high temperature solution to have the possibility to also measure them, where we today have to go with meters and measure at specific metering points. but we, yeah, this is what I was saying, yes. So most points of interest are well covered at pumping stations also with access to electricity. And we are undergoing this transition that Sigga described so well, but there the pipes are too slim for the constraints that we were given. But as I showed before, we have more district heating systems than only the capital area, and smaller district heating systems are sometimes located further away from other infrastructure. And yeah, it cannot be seen because of the border here, but we have then a region here below that is called Rangárveitur, which is further away from the capital city. But of course, it's the midpoint of their world, of course. And we have Ásalegur in Rangárveitur, which is a potential point of interest and is the case study that we located as the point of interest for this project and have provided data from the points where the green arrows are pointing. And the point of interest is where the red arrow is pointing. So the pipe is 150 millimeters, not quite within the constraints, but as close as we could with the fluid temperature of 65 degrees. So there we have the flow rate of 16 to 20 liters per second. And we only have the orifice plate flow meters at the user. So we don't have any data for that point today. If there's a leakage there, we would not know until somebody detected something wrong in the earth or something. So there would be an excellent example of where we could have this kind of metering. Yeah, and then there we would then want the power for a flow meter and pressure sensor. So that would be the case study in here. But of course, as presented, we don't only have the district heating network, we have also potable water system and sewage system. And within them, we see also further utilization possibilities. So existing springs situated in mountains far from infrastructure. How do I shift this? Like that. Here we go. New springs planned in remote places and pipes under the ocean are examples of places where the groundwater could use some metering. And in the sewage system, we have flow meters and level measurements in the wells, but they are powered by batteries. So that would be also another interesting point. So did I do something now? No? Here we go. It was just the thank you slide. It's the last one. But yeah, so what I wanted to say was also that that we are proud to be part of this project and see just the exciting 4 years ahead now in this discussion. Thank you. But thank you.
Yes.
Okay, so thank you very much. Okay,
You
here.
can just get the hand.
Okay, thank you very much. We have seen the possible application and of the outcome of the HOPE project, and now it's my duty and my honor to present what we are developing and what we want to develop in order to understand if we are on the right path for face these challenges or if we have to modify somehow our targets. Just a few words on the project itself. As you can see, it started in November 2022 with a grant of about 5 million. The consortium is composed by 14 partners, among which there are several universities, but also industries and potential stakeholders like OR and other. You can find the name over there. And the main target of the HOPE project is to exploit the untapped hydropower potential in natural and artificial water flows. I mean, for example, water distribution network, as we have seen, but also irrigation channels and natural flows like the ones that we have in for example, in the Lagoon of Venice in Italy. This energy is untapped for two main reasons. The first one is that the amount of energy available which can be exploited is limited. And I will show you some data later on. And the second aspect is that because of this limited amount of energy, we cannot use a standard solution like hydraulic turbines because they cost too much. And this is not sustainable for companies. So for this reason, we have developed a solution. We are trying to develop an innovative solution whose goal is to be sufficiently efficient, but also low cost. And the concept at the basis of the HOPE project is the one that is shown in this figure. If you immerse a body in a water flow, downstream, you create vortexes like the one plotted in this figure. And if this vortexes has the right frequency of shedding and the right intensity, you can produce vibration and forces on the bodies. And the result is what we can see in this video. The result is a moving body forced by the water flow, and you can try to extract the energy of the motion of the body. This is the general concept of the HOPE project. And to do this, we are developing possible configuration. Here you can see an example of the configuration we are considering for the piping application. There is a hydrofoil which will be inserted within a pipe, and we are trying to study the possible movement, the possible vibration generated by a water flow on this hydrofoil. And this vibration will induce a bending in the body. And with piezoelectric patches properly located on the body, we can try to extract electricity from the water flows. Of course, this is complex for several reasons. First of all, we have different application fields. I have mentioned them at the beginning of my presentation. There are water distribution network, wastewater treatment, and natural flows. So we have tried to classify all the possible application fields in three main groups, named piping, open stream, and open channel. Piping is quite easy to understand. We are targeting pipes in hydraulic networks like the ones that we have seen in the presentation before. Open streams means situation in which you have a water flow with a specific direction, and you can use also the walls to as an installation point for the technology itself. Whereas open channels means a completely open movement of the water, like in natural flows, for example, in the Lagoon of Venice. And for each of these applications, we are trying to identify the most suitable configuration. There are different options. All these options are under investigation and will be tested in laboratories in real operating conditions. So we need real operating conditions. And for this reason, within our project, we have several case studies which provided us a lot of data. We have 4 distribution networks in Italy, in Austria, in Spain, and moreover. We have 1 hot water distribution network, and we have just seen it. And then we have 1 wastewater treatment in Italy, 2 open channel application case study, and 1 lagoon. Of course, the Lagoon of Venice. And one of our activities is to collect as much data as possible from these case studies in order to define the boundary condition in which our technology will be required to operate. So Here are just some examples of the data we have already collected. For example, in the case of the piping application, we have seen that on average, the water flow velocity is between 0.4 and 2 meters per second. We can have different diameter of the pipes. As we have seen, we can go from 200 millimeters up to 2.5 meters of diameter, depending on the application, on the position within the networks. And there are also challenging operating conditions like the temperature. For example, in the hot water district heating networks, we have an average of 130 degrees, which can pose technical problems like the glue of the patches suffering at the high temperature of the water. So we need this data because this data provided us the right technical constraints and drive somehow the research activities in the right direction to make the solution really feasible and properly designed for the different application field. Here, some other data about the open stream case studies. As you can see, velocities are a little bit changing, dimension are changing, and dimension is an important constraint because we have moving bodies, and the space around the bodies somehow can create a constraint. In a pipe with 200 millimeters of diameter, the movement, the allowed movement of the body are limited because you cannot hurt the walls of the pipe. So these are constraints that have to be considered during the design and the development of the technology. And last but not the least, open channel application increases a lot the available space. For example, we have with ranges going from 6.4 up to 17 meters, which is good in terms of oscillation, but can pose problems in terms of water direction because not always you know the direction of the water, and you need to develop something that can be adapted to a variable direction, not only to a variable water velocity. So our scope, our goal is to produce energy. And to do this, we have to obtain a significant movement of the body. But this movement is obtained only if we are capable of achieving the so-called lock-in condition. The lock-in condition is a phenomenon in which the vibration induced by the water flows, by the vortexes that I have shown before, are perfectly synchronized with the natural frequencies of the body itself. So the natural vibrational modes of the body itself. You have to synchronize these two behavior, and you have to synchronize these two elements also with the control system having its own damping factors and its own influence on the system itself. And this is challenging, and it requires a design which is perfectly customized on the water flow characteristics. And another problem is that we have not constant water velocity in the different case studies. For example, here you can see one here of water velocity measurements in a water distribution network in Italy. And as you can see, the velocity range is quite wide. We go from 0.1 up to 0.9 meters per second. Each velocity requires a different geometries to obtain the lock-in condition. So if you design the technology for 0.9, it can work in the lock-in condition around that value, but outside that range, for example, at 0.5, 0.4, you lose the lock-in condition and the energy production drops down. And this is challenging because we have to find the proper design, the optimal design to try to maximize the energy production. But we have to be aware that our technology will not be able to produce electricity all the time. There will be instants, maybe minutes, in which we will produce energy, and other time ranges in which the production will be zero. We are doing our best to improve this behavior. For example, in terms of control system, we are developing the maximum power point tracking solution, which adapts the damping factor of the control system in order to follow the water flow velocity, in order to adapt the control system to the new operating condition. This allows to produce energy for a longer period, but we are not fully aware now of how long this period can be. We are studying on this. And the last problem, the last challenge is the amount of power. If you look at this graph, with the maximum velocity, so in this case, 0.9 meter per second, a rough estimation of the ideal power that can be extracted from the water is 140 watts. So we are not producing really renewable energy. This is not our goal. We want to try to extract a little bit of that power in order to feed sensors, in order to support digitalization of the networks, of the case studies under investigation. And we have to be aware and fair from the very beginning that, for example, in this case, 140 watts is totally unrealistic. We cannot extract all that amount of power. If we apply the laws known for the wind turbines, for example, it's reasonable with a high efficient system to extract the 40% of that power. But we have another goal, to make it low cost and to make it sustainable for a company. So we need to maintain the cost of the technology also at a lower value, at a low value. And because of this, the efficiency of the system is not expected to be as good as the one of a wind turbine. So this will further decrease our power. And we need information about the possible application. We need information about the sensor requirements. How much power is required by the sensors to install in the district heating network, to install in the water distribution network, because this will drive our research and it will be provide us data in order to understand if we are going in the right direction or not. The final goal of the project is to make cities and networks more resilient and more environmental friendly. So we are also in parallel carrying out activities in order to assess the environmental impact of our solution, the sustainability, the holistic sustainability of the solution, not only the ecological sustainability, but also the technical and economical sustainability. And to do this, again, we need your feedback. We need to have information from you about what also can be considered sustainable from an economic point of view, in order to have a range of potential cost of our technology to make it sustainable. So we are using the knowledge of our partners. A lot of meetings are ongoing with the companies involved within the consortium in order to understand their needs, their expectation, and all the information that they can provide us. But we need also to engage stakeholders, because we need their feedback and their data according to the things that I was saying before. Last but not the least, also the cost is important, as I said. So we are also investigating a low-cost manufacturing solution. One purpose is also to develop what we have called the do-it-yourself platform. So a platform in which even the society, a smart guy can find enough information to manufacture, of course, maybe in a rough way, but to manufacture its own device, maybe to install it in the irrigation channel passing through his garden, just to produce a little bit of energy for lighting up the garden. But this is the purpose, to maintain the cost low in order to make it sustainable for companies, but also for the general society. And this is all. Thank you.
No. Perfect. I think we're just right on time. We just went a bit over, but first of all, I'd like to thank our speakers for today, Livia, who was as well as Giovanna and David for organizing this session. And of course, feel free to stay on and continue here. But in the meantime, we'll close the session and close the webinar as well. And thank also our participants for joining online. And yeah, we'll be definitely sending this over and sharing this, and so that we have a good feedback session from this. But thank you very much for this, and hope to continue discussions further. Thank you.